Good morning, evening, afternoon, whatever the case may be. This is Dr. Buckley. I thought I'd put together a short presentation for you about the upcoming experiment on Avogadro's number. And so I'm going to go through some things. You certainly have the lab book. You ought to read that. Take a look at it. Make sure you know what you're going to be up to on here. But as we go through here, we'll go ahead and kind of give you an idea of what things look like so you can get a feel of it, and hopefully you can work pretty efficiently in the laboratory. The lab book looks like this. You should have that already from the bookstore when you go to lab. This is a February 2015 printing. If you're watching this in a different semester, then you're going to see probably a different color on top of the lab book. There are two parts in Avogadro's number experiment to look at. One of them is sort of an original part for us that we're going to look at modeling it using things that we can see and feel. In this case, metallic and glass spheres. We'll be looking at trying to figure out something about what Avogadro's number is all about. And then we're also going to look at experimental determination of the value of Avogadro's number using stearic acid solutions. That one's been tried before. That's in the literature and seems to work pretty well. So we're going to go ahead and get you set up here and see what we can figure out. Lost my mind. If I take a look at this sphere here, we'll start with him. And if I want to find his mass, instead of just weighing one of them, what I'd like to do is weigh one and maybe two or three, and then maybe 5 or 6 or 8, or maybe 10 or 12 or 14, and get masses of multiples of those, and construct a plot that's going to be a plot of the mass of those versus the number of spheres I have. The slope of that plot that you make is going to be the mass per sphere. That's going to use all the information, so it'll be the best value you can get based on what we've got, considering we're using a hand plot. And so we'll go down here below. And once we have a mass for these spheres, we're going to figure out how many spheres it would take to make this many grams of Avogadro's number. I'm sorry, never mind. How many of these it would take to make this many grams, period. So if I want to get 3.21 grams of this, how many of those spheres? If I want to get 11.04 grams, how many spheres, and so on all the way across the road. This is very similar to what Avogadro's number does for us. Now, Avogadro's number is a lot bigger than what this number is going to be. I made up a name for this one, and I couldn't think of anything better, so I just call it Avogadro's number, named after Cameron, obviously. And so it's going to be a whole bunch different than Avogadro's number, but the idea will be intact. When you do the post lab, you'll see a little bit of working with the spheres and see a little bit of working with the actual periodic table. So these are the these containers are set up. You're going to find out your containers will be probably much smaller than this, but you'll have several of these spheres inside of them so you can work with them. The elemental symbols here are all fictitious. I made those up on my own. They actually stand for something a little bit, I think. This is the small spheres. This is the glass spheres. This is the medium-sized chrome steel spheres. This is tungsten carbide, and those are large ones. Just so it's not actually totally random. These two here, be a little careful, ME and WC. These guys are very similar in size. The WC has a little bit different look to it in terms of coloration than what the ME does. And the tungsten, the WC, is actually just a touch, like a 64th of an inch smaller. But when you work with these guys, try not to get those two mixed up because they have very different masses, even though they're very close to the same size. Now, we're going to look at using the balance to start with, just kind of get an idea of how this will work, how we're going to gather the data. It will take very little time to gather these data. It may take a little bit longer to process them than it is going to take to actually gather them. We use Scout Pro balances. These are the ones in the freshman lab, General Chemistry 1 laboratory. We also have some balances down the hallway, which we will use from time to time. I don't know if you'll use them this week or not. It just kind of depends on how many you have in your lab and whether they're available and all sorts of things there. These balances are not as accurate as ones down the hall. These are certainly adequate enough for what we're going to do today. You notice on here that there's really just two buttons, on, 0, off, and over here, print and unit buttons on that side. These are not hooked up to printers, so that button doesn't matter for that. You might want to watch the unit thing a little bit because you don't want to end up with, you always want to end up with grams inside of there. So let's take a look now at how we're going to go about doing this. Turning these on, very simple. Hit the on button, not too hard at all. Hit that, looks like that. When it first comes up, it'll read 0. I unfortunately didn't include a picture of that. And now I've put this beaker on top, this plastic beaker on top, and the plastic beaker on top is there because what the plastic beaker will do is that's going to hold our spheres. You notice if you laid these spheres on top of this balance, they're liable to roll off somewhere, and then we'd have spheres all over the place and it'd be a mess. So we put that beaker on top, but what I want to do is make sure that whenever I get the mass of just the balls. Now I could write down the mass of the beaker and I could subtract it out every time, but the other thing I can do with it is I can use this button here that says on, 0, and off, and I can use it to tare, okay, the balance. And tearing, notice it's T-A-R-I-N-G is tearing, or if I want to tare the balance, it's T-A-R-E. And when I hit that button, what will happen is I'll get a screen up that'll have this beaker on it, and it'll say 0. So I've read it out, now this beaker's on here, it's reading 0, so anything I add on will just be seeing the mass of that object inside of in our window here. When you use these balances, any kind of electronic balance, write down everything, all the digits here. We've paid for all of them, so write them all down when you get a hold of them. Also notice out here where the G is, that's gram units. If this doesn't look like a G, press the unit button until it does, because you want to make sure everything you do is in grams, and that's true today, and that's true through the entire 2-semester sequence of General Chemistry 1. There aren't really any cases where we're going to go measure in newtons or strange things like that. So what you see here is I've got one sphere thrown in here. You can kind of see him up in this size over here. He's reading a mass of about 8.41 grams. So you can take and record in your book that this is one sphere has a mass of 8.41 grams. Then we're going to throw in some other, it doesn't have to go 1, 2, 3, 4. It's better if you stretch them out a little bit. And so here I've put in 4 spheres. Okay, right there. And if you look in here, there's 1, 2, 3, 4 of those. Their mass is 33.49. I write down, hey, that's 4 spheres, 33.49 grams. Then I add some more in, so I'm up to 6 spheres piled up inside of my container here, and the mass now is reading 5020. There's 13 spheres, and you can try to count them if you want to, but it doesn't matter. And the mass of those is 108.74. So when I get done doing all that, what I've got is a set of data. So I have one sphere had a mass of 8.41, 4 had that, 6 had that, 9 had that, 13 had that. The 9 I didn't show you a picture of, but it looks like the one in between a 6 and a 13. Those are our data. What we want to do is make a graph of these things. We want to understand what it is, what the mass is per sphere based on. So you could think of different ways of doing it. You could add up, you could take this and divide 33.49 by 4 and get an average there and kind of average that. You could do that, but you'll find out there may be small variances, probably not very big, but some small variances and that sort of thing. So what we want to do is use graphing in order to figure out what these things look like. A note on graphing terminology, and this will be with you all semester long into Chem 2 and anything else you get into, is when you hear somebody saying make a plot of y versus x, or speed versus time, or mass versus number of spheres, or gallons per dollar, or whatever it's going to make, the y is always the vertical axis. It's always the one that goes right here vertically on that axis, and the x is always the horizontal axis. Don't get those mixed up. You know this from arithmetic, from algebra, sorry, not arithmetic, from algebra, that y is your vertical axis, x is your horizontal. It's always represented in the form y versus x. And so when we tell you in here, we're going to tell you to take and plot the mass of these spheres against the number of spheres. We're talking about the mass being vertical and talking about the number of spheres being horizontal. If you have trouble remembering that, just think of it this way. We read left to right, don't we? So here's my y, here's my x. So if I just take and think of left to right, my y comes first, and then my x comes. Okay, it follows quite naturally. You will find graph paper in the back of your book. It looks something like this. This is not one of the best shots of it you'll ever see. And if you take a look at trying to figure out how to plot a graph on here, you want to take a look at how many boxes you have to work with. And across the bottom of this, you have 35 boxes, and going up here, you have 48 boxes. There's my 35, there's my 48. What we want to do when we make a graph like this, we want to use more than half the graph paper in each direction. But we want to choose a spacing, a grid spacing that's reasonable to plot and to read. You don't want to make it too difficult. An example here. We had 13 balls. If you go back and think, there were 13 spheres that we had was our most. And we want to plot those along this axis along here. So if I took 35 boxes and said, okay, I have 35 boxes, 13 spheres. If we're going to make a box, each be about 13/35 of a box long, and then be 0.37 spheres in each box, we could use the whole bottom axis. That means that this point right here is 0.37. This one is 0.74. This is 1.11, and so on. A really, really inconvenient axis. So instead what we say is, well, think about this. We have 35 boxes across. We've got to get all the way up to 13 in terms of our number of spheres. If I take 35 and divide by 13, I can make them be 2 boxes. for each sphere, and everything works out great. So if we take a look at the next page then, looks like this. I'm going to go in, and on the bottom axis I made little tick marks here. So that's 2 boxes is 1, 2, 3, 4, 5, 6, 7, 8 all the way across. Then I get all the way to 17. I only need 13, but I marked it all the way across. And similarly for my mass axis, I had to go to 108, and I wanted to get over halfway, and so what I did in there is I made 4 for each one of these. Okay, so I got it up to that point. And you might also notice on this graph that I've labeled this. Now I'm using a Sharpie so you could see it, so it's not as neat as I usually write. And this is a mass in grams up here, so I label the axes when I put these things down here. So everybody looking at the graph knows here's what this axis is going to be. You notice that these points going all the way up here are a pretty straight line, aren't they? So let's take a look at this now if I take and draw a straight line on there. So I take a straight edge, and obviously I didn't have the world's best straight edge or best coordination or both. Going up here looks like this. That looks wonderful. Everything's wonderful up there. That's my slope. It tells me how my mass changes with the number of spheres that I have inside of here. So you draw the best line you can. The best line means you're kind of cutting maybe above and below some of them. You kind of average it by eye, that sort of thing, and you come into here. Now what I have to do is find the slope of that line. So when I take a look at it over here, what you'll see is this is the old rise over run thing you might remember from math. I pick out a couple points on the line, and they don't have to be actual data points. Don't pick one of your data points, because if you do pick a couple data points, there's no point in having done any of this except for those 2 data points. Pick a point on your line that's not a data point where it kind of crosses an axis. So I picked out up here. I said, okay, that pretty well crosses an axis in there. And I come down to here and pick another one. This guy kind of crossed right where the crosshairs are down here. And this is the old rise over run thing. The rise is, how big is this? He's at 88 grams if I read over my axis here. And I'm going to subtract off however many I have at the bottom, and it's going to be like 4 grams. So I have like 88 minus 4 grams is 84 grams. That's my rise. My run is going to be whatever number of balls this is, and it looks like it's 10.5. You say, wait a minute, you don't have a half a ball, and my answer is nobody cares. It's at 10.5, you're going to go down to about a half. So the number of balls there is 10.5 minus a half, gives you 10. So my slope is rise over run. 84 divided by 10 equals 8.45 grams per ball. And that's pretty close to what we had in the first ball, which was 8.41, but we're making you do this to get an idea of graphing. Okay, so you could do this thing in Excel. We'll show you how to do that pretty soon. It won't be too long. You'll be doing it in Excel. You get very nice values for the slopes and uncertainties and all this type of thing there. And so here's my final graph. I don't want to put a second one in. It does give me an opportunity to point out you need to have a title on your graph too. So you have to label the axes along here. You have to have a title on it. And the title is not just mass versus number of balls, because anybody can look at that and see that. You want to be a little more descriptive. What is this? In this case, this was the LE mass determination. It was the element LE that we're finding the mass of. And so I've got my mass now. It's 8.4 grams per ball. And then what I can do is go back and use that. I can use that in that periodic table from before to say, okay, how many of these balls would it take to get to that atomic weight in grams? And we'll see what that number looks like. Expectation is it'll be around the same no matter which ball you had. That's what Avogadro's number does. And the second part, just one quick slide on the second part. It looks something like this. This is a stearic acid molecule over here. Okay, so he's got an end on here that's, we say this is hydrophilic, means it's water loving, and it's hydrophobic up here. This is very much like your soaps and detergents. What happens with soaps and detergents is they stick this end up here into greases and oils and things like that, and they stick this end into water and it rips the grease and the oil out of your laundry. So it's kind of a handy thing. Well, what's nice about this is when I put him into water, he actually will stand up like this, sort of like a stalk of corn. He'll stand up like this. Here's my simplified view of it. If I thought about this molecule across the bottom here, he's got sort of a square end on him, and his cross-sectional area is 20.7 square angstroms. And if you brought it over here in kind of the bigger picture thing over here, we're going to take a petri dish. A petri dish will be 4, 8, 12 centimeters across, something like that, whatever petri dish you have. You're going to put water inside that petri dish until the water is really just concave on top. Okay, so you can actually, convex on top, so it's actually sticking up above the petri dish a little bit. What will happen is you add more and more of these molecules to it. We're looking at them end on. These guys are standing up, pointing right at us. We're looking at the hydrophobic end, the one standing up out of the water. And they'll kind of line up like this and fill up and fill up and fill up. And when the last spot is filled up on this circle, then the next time you put a drop of this stearic acid solution in, he suddenly can't go anywhere, and he's going to form sort of like an oil slick on top here. It's pretty neat. It's kind of neat to watch. So the idea is that we have some idea that if we know how many moles of stearic acid we put on here, and we know what the cross-sectional areas we do over here, then the number of molecules in that picture is going to be whatever the area is in square centimeters divided by this 20.7 times 10 to the minus 16 square centimeters. That's 20.7 angstroms, but I put in square centimeters to match up here. And we'll get a number for Avogadro's number, and these generally come out pretty well. So that's a quick rundown on experiment 1. I hope it goes well for you, and certainly let me know if it doesn't. You can get a hold of me at gbuckley@cameron.edu or drop into my office in 225 G, or I might even see you in class. Who knows? Good luck with it.